So what we've talked about this week and a little bit of last week was, from my dice example, was the idea that for some data like dice, we know that there is an underlying distribution that looks fairly normal, where we should have an expected outcome. So when you roll 2 dice, the expected outcome is 7. Why 7? Well, it's the mean of all the other outcomes. It is also the one that has the highest probability of happening. But in our examples, when you guys threw a round of 6 dice, or 6 rounds of a pair of dice, you ended up with an average score of like 9. And then I said, well, you guys are doing it wrong, because 9 is definitely not 7. And then so with some assistance, I rolled the dice and got to 7-ish, 7.6. And I said, it's just that I'm better at this than you. Well, we're gonna do some math a little later to see, using what we already know with z-scores, how probable was it that I got the outcome that I got versus the outcome that you got. But in order to get there, we got to finish this idea of what happens to things like the mean or the standard deviation or the variance when we think about them in terms of our sample. So when we were talking about variability, which is how we use the standard deviation, for example, we talked about, well, if you have high variability, your curve will be rather flat, like sample B. But if you have low variability, your sample will look more like A, where you have lots of cases around the mean. Okay. When you do this with a sample, this has a new term. It's called the standard error. Right? The standard error. And the standard error reflects the idea that our variation is impacted by the number of observations that we have. So let's look at these 2 curves. Normal-ish, right? We got one with a really, really long tail. And then we have another one that has about the same hump to it, but a shorter tail. This is a sample of income. In fact, they're both samples of income. The only difference between the 2 is that in the first one, we happen to sample Bill Gates. Insert actual rich person there if you don't know who Bill Gates is. Mark Zuckerberg. Okay. In our sample, what happened is we got somebody that's a bazillionaire. And what happens? Well, that one person is going to stretch out our data. Well, if we were to do a smaller data set, all right, a smaller sample, the potential for our variation to get that stretched out is going to be smaller. Right? And so, yeah, you might get a couple of people that make a little bit more money than the typical person, but you're probably not going to hit Bill Gates kind of money or Oprah money, right? Or Mark Zuckerberg or some Russian nickel tycoon. Okay? You're not going to hit them. Saudi prince. Actually, they're probably not more down here by now. Price of oil cratered. Okay. So because of that, the chances that we're going to get somebody way out here with a smaller sample diminishes. Okay. So what we do to account for this sampling size is when we compute the standard error, we build into it the number of observations that we have. I should have more notations here, but right. So our standard error, because it's not standard deviation anymore, we're talking about a standard error of like a mean, our sample mean. Is equal to the standard deviation divided by the square root of our sample size. So the standard error is equal to standard deviation divided by the square root of the sample size. So let's think about this. What happens to the standard error as n goes up, as we have more and more and more observations? It goes down. Why, Jake?
Because more possibilities can get.
Maybe. Let's think about this. Pick a random number between 1 and 10. We have two samples. As n increases to a ridiculously large number, versus a smaller number. Came prepared today. Didn't want to fumble with my phone. 5 divided by the square root. Just turned my calculator off. The square root of 93746. 436. Is a tiny number. The standard error of 5 divided by 400, a sample of 436, 0.24. Okay. So, one more time. The larger our sample size, the smaller our standard error. That makes sense because we're talking about how close we are to representing that population. If you had a sample of 2 people to represent all of America, those 2 people, let's say your parents, bio mom and bio dad, close your eyes. What would that tell you about something about America? Are they average? Are they typical? Or are they weird? Right? Imagine Abigail, all right? Abigail, my daughter, if she were to take the traits of her parents, what would they have? Well, let's see, PhD and multiple graduate degrees. We would overestimate the levels of education of Americans. Right? But if we were to take the parental qualities of every coastal student, anybody here, parents just have a high school diploma? All right, we're getting closer, right? That's a better representation of everybody. So as n gets bigger, our error should get smaller. So again, if we think about it as n gets bigger, like the difference between an n of 25, which will have this sort of big curve, and an n of 20 2500, which will have a smaller curve, our sample mean, so that number that we have gotten from our sample to represent our entire sample, should be closer to the population mean. So this is, again, our example about income. Right? Because we know that there are super rich people. Also known as FU rich. You have so much money that you have FU money. Okay? There are those people out there, but there's not that many of them. So our sample is less likely to get them in our sample. But the more people we get, the closer our sample mean, our x bar should get to the true mean, which is mu. Yeah? Everybody's quiet, and it's either because I completely lost you, or you're like, I'm cool with that. Which one is it? Okay, nobody wants to say anything. Now, we can do this, right? We're going to, using our z-score framework that we already know about, the difference divided by something gives us a z-score. To compare our samples to a population. Okay. So let's say we know the population values. The population for a car price. Right? The average value of a car is $12,000 with a standard deviation of 4,000. So most cars are worth between 8 and 16,000 for one standard deviation. That's what, like 68%. If we do 2 standard deviations, which is 95% of the cars, then it's somewhere between 4 and 20,000, right? Using the empirical rule. But we've got a sample of 625 cars. Okay. I lost something. Which sampling distribution is for a sample size of 625 cars, and which is for 2,500 cars? So we just learned something, right? We learned that as n goes up, what should happen? That sample mean should, not the mean will go down. What should the sample mean do? We're not, yeah, pretty much, but what should that curve do? Which of the two curves represents which number? All right. Why? That sample mean should get more compact, right? Our sample should be narrower. Because again, we're trying to approximate the population. So that sample mean will get less variable. Right? There'll be less area around it. It'll get more compact. It'll get smaller. The numbers are going to stay the same. Right? We could go out and, let's see, 625. We could go to the overflow lot over by the Frisbee golf course. Right? 625 cars. Look around and go, okay, commuter cars, yeah. Right? And this is our value. Or we could look at every car on campus. Now, what are we more likely to do if we hit every car on campus than if we only look at the commuter lot? How is our sample going to be different? Right, it'll be closer, but why? What is it about every car on campus versus just the commuter lot?
Represents a greater population.
Bigger population. But tell me about the nature of that population. Let me reverse the question. Who are we not likely to see their cars in the commuter lot? Faculty, right? Are faculty parking in the commuter lot?
Some people.
Well, if they got like, they're in Baxley or something. Or if they get here a little too late. They're on that side of campus. I have never parked in the commuter lot, except when I'm too lazy to walk over to the registrar's office and I drive over there. But then I try to sneak into the visitor parking for a little bit. But, things happen. Okay? So if we just have a smaller sample, chances are that sample won't be representative. Now, unfortunately, at Coastal, a lot of you all drive better cars than we do. So, there's that. So I drive a Chevy with 100,000 miles on it. And if we did the math, right, the square root of 625 is 25. $4,000 divided by 25 is 160. Versus doing the square root of 2,500, 4,000 divided by 50. Right? We can see that this peak is going to get smaller, and our sample mean, the distribution of our sample means should get narrower as well. Okay? Okay. So let's shift gears just a little bit. Because now that we're talking about populations and samples, and we're going to have a framework where we can have our sample and the data that we collect in our sample, if we want to go beyond describing it, and we start to want to make decisions, or we start to want to make claims based upon that data, we're going to have to introduce the idea of probability into it. So we have to make that connection between our sample and the greater population. You see this, particularly if we're talking about politics, you will see this pretty much every day for the next, it's not soon enough, 51 days or so of the presidential election. Anybody see the poll of the day today? Anybody know what Clinton's margin is now? There's a new one. It was the first poll out after the debate. No, Clinton's up +3. Before the debate, it was Trump +1. So we think we've seen a 4-point swing because of the debate. That's the national poll, which isn't the right way to do it because of the Electoral College, but still. However, in the little tiny print at the bottom of the TV screen, it'll say margin of error, ±3 points. That's because they recognize that they have a sample. And using the empirical rule, right, that ±3 points is telling us that the standard error is 3. Okay, that's what they're telling us. That plus or minus, that margin of error, that is solely based upon the population size. So if you want to have a poll that has a smaller margin of error, you need a poll that has a smaller standard error, which means you need to do what to the n? Make it bigger. Make it bigger. The night of the debate, on Monday night, CNN had what's called a flash poll. What you do is, after an event happens, the second after something happens, you get a polling outfit like Gallup to try to get a national sample as quickly as possible. There's a great episode of, is it The West Wing? There's a great episode, I think it's of The West Wing after a State of the Union. and basically the episode starts when the State of the Union is over, and you see everybody at like the polling station, at the place where they're doing the polling, and they're just itching. What's our sample size? What's our sample size? What's our response rate? Right? So as I'm watching the debate on Monday, CNN has a flash poll. The debate's over. The National Opinion Research Center, NORC, gets on the phone and they start calling people. And it takes about half an hour. It was about half an hour. And after half an hour, they were comfortable with the sample size that they got. It was like 524 people. And they said, according to our flash poll, they didn't call it flash poll, according to our survey, our poll, Hillary Clinton won the debate according to 62% of debate watchers. Okay? Margin of error, 4.5 points. Now, the gap between the 62 and like the 24 that I think Trump got was big enough so that if you took away 5 points from Hillary, that's still 57%, right? But it was that large because the N was so small. It was only 500 people. Typically, we like to get about 2,000 people. Anywhere from like 1,200 to 2,000 will give you a margin of error of about 3 points. Okay. That is statistical inference. We're using our sample to say something about the population. We kind of already know how to do this stuff. We just had to adapt what we've done before to our new way of thinking about samples versus population. So in our dice example, I showed you the picture of the dice. We know that the expected outcome, the mean outcome, should be 7. You all did it and you got a 9. How likely is it that you will get a 9 when you should have gotten a 7? Well, you already have the framework for doing this. If it were a different type of question and I gave you numbers and drew the little ticks on the curve, what would your next step be? What would you try to find? I want to know the difference between a 7 and a 9. Okay, so you would probably try to find the area that represents this 9, which involves what? Finding a z-score. Okay, so now what do? It's a z-score. What's usually the numerator of a z-score? The difference between one mean and the other mean. All right? Or the difference between the two numbers of interest. So what should I put first, the 7 or the 9? If I'm subtracting these. Why? What kind of a z-score am I going to get? A positive one, right? Because it's on this side of the number. Okay. 9 minus 7. What's the next thing? What do we put in the denominator? Usually the standard deviation, right? But what is the standard deviation when we're dealing with a sample? It's the standard error. Okay? So we have to put the standard error divided by the square root of our n. What's our n? Thinking back to this particular example a couple of days ago. How did I get the average of 9 by having 6 people roll dice? Professor Wood, you still got number up there that's not really a number. All right? Did some Googling. Found out that the standard deviation when rolling 2 dice is 2.412. Okay? And the square root of 6 is 2.45. .412 divided by 2.45. That gives us a z-score. So I just did the math, right? Square root of 6 is 2.45. Divide the standard deviation divided by the square of n. Gives me 0.98. 2, because 9 minus 7 is 2. It's the difference. Divided by 0.98. Z equals 2.04. Now what do I do? I do what? Somebody pull out their chart. What is the area of a curve for a z-score of 2.04? 0.9793. How likely is it that when you roll set of dice 6 times that your average is 9? How likely is it? Not very likely, right? You guys suck at this. That was the conclusion, right? Let's replace that 2 . Let's replace that number that you guys got with my 7.6. What is 0.6 divided by 0.98? That's equal to a z-score of 0.61. What's the probability of a z-score of 0.61? My 73% versus your 97%. So who was better? Me. Why? Because it's the distance away from the mean. I forgot to subtract the 5, right? Minus the 5. I was much closer to getting the 7 that you should have expected to get versus the 9 that you guys got. And if you think about it in terms of probability or area, you can see how much closer I was. The difference is about 0.25. 25% better than you guys. It's so not the way you use these numbers, but it sounds good, right? So mine was more closer to the mean with my 7.6 than your 9. What's the question?
Where did you get the 0.6 from? Like when you added like the 0.6?
Well, when I rolled 6 die, right, 6 pairs, my average score was 7.6. And so that is my sample mean. My sample mean was 7.6. You all's was 9. You got it? So 7.6 minus the expected 7 leaves me with a 0.6 in the numerator. The standard error didn't change at all because we both rolled 6 pairs of dice, right? So our n was both 6. So that's why I just changed the part up top. Okay? So we can talk about comparing two groups, right? The mean of students, which was 9, and the mean of faculty, which was 7.6. We can start having that discussion, but what we have to learn how to do is to take these areas and turn them into probabilities. And the way we're going to do that is from the science.